Hello and welcome to lecture 28. Today we are starting with module 6. In last week we were discussing about turbofan engine. We started discussing what all are the needs for the turbofan engines. Then we have done the classification for the turbofan engine. We also have discussed about the construction details. Then we were discussing about the high bypass ratio engine, low bypass ratio engine. After all this understanding, we have started with the very first type, that is forward fan unmixed single spool configuration, where we have discussed about the effect of various cycle parameters on the performance for both design as well as say off design condition or the cruise condition, and we try to understand the effect of various cycle parameters, how it will be changing with say different performance parameters. Now, from this week we will be discussing about the next configuration, that is forward fan unmixed two spool configuration, where we will be discussing about the fan and low pressure compressor. They will be placed on one shaft and high pressure compressor that will be on the other shaft. Second configuration we will be discussing, that is for fan driven by low pressure turbine, compressor and high pressure compressor that will be driven by high pressure turbine. Then we will be discussing about the effect of various cycle parameters on the performance for say design as well as cruise condition. So, let us start with, in our classification, this is what we are planning to discuss in this week. So, here if you look at it, says my fan and low pressure compressor, they are on one shaft. So, we must realize here we are having two spool configuration. Same way, second we will be discussing about the fan that will be driven by LP turbine and compressor will be driven by HP turbine, that is also two spool configuration. So, let us try to understand what we mean by two spool configuration for the turbofan engine. So, what all we have discussed for turbojet engine in terms of single spool configuration and two spool configuration, the logic is similar here. So, over the year, as we have discussed, there is a requirement for higher and higher thrust. Later on, people they have realized in terms of lower specific fuel consumption, people they started talking about the fuel economy, and that is what has given some innovative ideas in terms of configuring the turbofan engine. So, one of the configuration here, if you look at, say we have fan and this are my compressor stages, they are being run by LP turbine. Here inner side also, if you look at, we are having say compressor stages, they are being connected with my HP turbine. So, like what all we have discussed for the turbojet engine, similar configuration it is applied here. So, very first after fan, what compressor stages we have, people they are defining that as say LP compressor, sometimes they used to say booster compressor, and these compressors they are different from the next stage compressors. These compressors are say our HP compressor. In between these compressor stages, we are having the diffuser that will diffuse the flow and will try to maintain the pressure to be constant, total pressure to be constant at the entry of the HP compressor. Later we are having our combustion chamber. The function for this combustion chamber is similar to what all we have discussed. The next components what we are looking at, they are say HP turbine, then we are having LP turbine, tailpipe and nozzle. Here in this we are discussing about the unmixed configuration. So, we are having two different nozzles. So, here we are having one nozzle, that is what we say as a core nozzle, and second nozzle that we say as a say fan nozzle, and here this all are representing the stations. So, I prefer, like let us say if I want to represent the process on TS diagram, you have all these stations. You just try to put these stations and different processes on TS diagram. Let us look at, suppose if I consider we have this as our entry pressure. Very first component with what we have is our say diffuser. So, this is representing the actual process. Next we have is our fan that will be compressing the air from station 2 to station 10. This is representing our actual process. Now, you are familiar with what we mean by ideal process and what we mean by actual process. Next we have is my LPC. So, it is called low pressure compressor. So, this low pressure compressor that is represented from the process say 10 to 3. Be careful, as we have discussed earlier also, the air which is coming out from the fan, that will be having rise of pressure. So, rise of pressure will be from station 2 to station 10. So, some of the air that will be bypassed through this nozzle and some of the air that will be entering inside our core engine. So, my entry pressure will be P10. So, do not get confused with this part. The next component what we have is our HP compressor. This HP compressor that will be raising the pressure from 3 to 4. The combustion process, as we know, actual combustion process is different from the ideal combustion process in terms of drop of pressure, and that is we are representing here. So, this station 5 is a maximum turbine entry temperature. With that temperature and pressure, the flue gas that will be entering inside our HP turbine. So, here this is representing our actual expansion process from process 5 to 6. Similarly, the next expansion which is happening inside my LP turbine, it is represented from say process 6 to 7. We have our tailpipe. So, where we are considering there is a drop of pressure from P07 to P08, and from there the flow that will be exit from the nozzle, and that process is represented by process 8 to 9. In line to what all we have discussed for our first turbofan engine configuration, the air which will be coming out from station 10 or at the exit of the fan, that will be passing through the nozzle, fan nozzle, and that expansion process we are representing from process 10 to 11. So, I am sure you are now familiar with what all we are discussing in terms of representing the cycle on TS diagram. So, it is preferred what configuration is given to you, based on that just plot this line diagram, and from that line diagram try to plot your TS diagram. So, it will not give you any wrong information or you will not get confused with. Remember, this whole course it is for the gas turbine cycle. So, we are having number of cycles, number of configurations are possible. So, as we go ahead you will be having many cycles, and that is what will be putting you in confusion. So, it is preferred read the information carefully. Suppose say here it is clearly mentioned fan and low pressure compressor, they are on one shaft. So, the meaning here these are on one shaft. Okay. Now, GE CF6 engine series, they are of this configuration. Same way Pratt and Whitney 4000 series, they are of this series. So, here I am putting you one assignment in terms of collecting the data. You are requested to collect the information about what all are the companies or which are the companies which are making turbofan engines. So, just try to list the name of companies, just search through your book or maybe through internet, just try to collect which are all are the companies which are making say turbofan engines. Okay. Now, let us look at what we mean by this. So, here this is representing the cut section of Pratt and Whitney 4000 series engine. So, here if we look at, we are having big size fan. It says it is having diameter of around 2.8 meter. So, you can imagine the size of this fan. The next component what we have, these are say our LP compressor or the booster compressor. So, you can see here it says we are having 7 stages of this LP compressor here. This is representing my duct or diffusing duct, and later part, as we have discussed, this is my HP compressor. There are total 11 HP compressor stages that will be followed by the combustion chamber. Here we are having say HP turbine, and we are having around 5 LP turbine stages. So, this is representing the Pratt and Whitney engine, and that is what is capable of generating the thrust in the range of 344 to 408 kilonewton. So, you can imagine this is a huge engine, that is what has been used for say big size aircraft. Okay. It is having bypass ratio in the range of 4 to 7. Same way here, if you look at this is representing CF6 engine, where it is having diameter of around 2.19 meter, bypass ratio is around 5.72. We are having fan that will be followed by one stage of LP compressor, and then we are having total 16 stages of HP turbine, HP compressor. That will be followed by the combustion chamber. We are having 2 stages of HP turbine, that will be followed by the 5 stages of say LP turbines. So, just try to look at, try to understand. If you recall, when we were discussing in week 2, we have discussed why we are having this kind of shape, what we mean by low speed, what we mean by high speed, what we mean by LP compressor, what we mean by HP compressor. Let me put it, let us recall. LP compressor means operating pressure is lower, that is why it is called LP compressor. It is not that it is generating lower pressure, be careful. Same way, HP compressor means its operating pressure is higher. So, here if you look at here, my entry pressure it is lower, that is why it is LP compressor. Here, because I am having number of stages, that is what will lead to increase the pressure. So, operating pressure compared to your LP compressor is higher, that is the reason why it is called HP compressor. Similarly, for the HP turbine, the operating pressure and temperature they are higher, that is why it is called HP turbine. Similarly, for say LP turbine, since its expansion process, say turbine it is doing the expansion work, that is the reason operating pressure for LP turbine that will be lower, that is the reason why it is called LP turbine. Now, you are matured enough with all these configurations. So, let us see like other kind of configuration. This is a small engine, we can say that is what is being used for say small business jet engines. This is in collaboration with GE and Honda, it is called HF120 engine. The beauty of this engine, you can say it is having diameter of around 1.51 meter, it is having wider chord blade, that will be followed by this, all are say LP compressor. So, 2 stages of LP compressor, that will be followed by centrifugal compressor, and here we are having say reversible combustor, that will be followed by HP turbine and LP turbine. So, this is also of this configuration what all we are discussing at this moment. Okay. Similarly, this is with the saffron, it is called silver crest, and that is having say wide chord fan, that will be followed by 4 stage of LP compressor, that will be followed by 4 stage of HP compressor and centrifugal compressor, and later we are having one HP turbine and 4 LP turbines. So, just look at, so this all are the new configurations which are coming with. The difference here is in terms of use of compressor. So, most of the engines they are having axial flow compressors, but there are special requirements where we are looking for our engine size, weight and the length of the engine to be smaller. In this configuration we are using centrifugal compressor in place of axial compressor. That is what we will be having lot of benefits in terms of overall size, weight and length of the engine. So, let us see like what all we have discussed. Let us try to understand how do we calculate our cycle parameters. So, here in this case, this is representing very first process from infinity, that is atmospheric air, to 2, that is our intake or the inlet, and we know we have our diffuser efficiency we have defined. So, based on that diffuser efficiency, we can calculate what will be our exit pressure from the intake. It is a function of Mach number and diffuser efficiency. Similarly, since the process we are considering as a adiabatic process, and that is the reason why outlet temperature, that is given in terms of say Mach number. Okay. So, based on that we can calculate what will be our exit pressure and exit temperature. So, if you recall in last week when we were solving the numerical, we were given some different configuration, where in place of diffuser efficiency, total pressure recovery factor was given. So, be careful in terms of all those terminologies, and in order to brush up it again, just visit week 2 again, that will give some more idea and you will get benefited with what all need to understand for. Let us move towards the next process. That process is my forward fan. The process is represented by 2 to 10. So, we know what is our fan compression ratio. Based on that fan compression ratio, we can calculate what will be the exit pressure from the fan, it is P010. Same way we have our formula for say fan efficiency. Based on that we can calculate what will be our outlet temperature. So, outlet pressure and temperature from the fan, they are of our requirement. Now, this fan, as we have discussed, here in this case we have single fan. Maybe if we are talking about the low bypass ratio engine, it may be having fans. Okay. So, under that configuration polytropic efficiency terminology will come. Now, let us look at the next configuration, that is our LP compressor. For LP compressor, we may be knowing say our compression ratio, we may be knowing our efficiency. Based on that we can calculate what will be the outlet temperature and outlet pressure from the LP compressor. Okay. So, like for this LP compressor, since it will be having number of stages, so sometimes maybe in place of given you isentropic efficiency, polytropic efficiency may be given. So, do not get confused with this terminology. When you are having your polytropic efficiency coming into the picture, then you need to use this correlation. Okay. Now, let us move towards the next, it is our HP compressor. For HP compressor also we are aware of say what is our compression ratio. Similarly, we also know or we can assume what is our efficiency, we can say isentropic efficiency of the HP compressor. Based on that we can calculate what will be our exit pressure and exit temperature from the HP compressor. Now, let me put the words here. Suppose if I consider I want to calculate my overall pressure ratio, then this overall pressure ratio will be P04 by P02. It is nothing but the compression ratio of HP compressor multiplied by compression ratio of LP compressor multiplied by compression ratio of fan. Be careful, it is not summation, it is in multiplication. Okay. So, that is what will be giving us idea about the overall pressure ratio. Now, let us try to look at say next configuration or next component what we have, that is suppose say combustion chamber. For this combustion chamber, we know there will be drop of pressure and this drop of pressure will be in the range of 2 to 5%. So, we can calculate what will be our outlet pressure. We can calculate our fuel air ratio if my turbine entry temperature is known to me. Here we have discussed again and again, we can plot the control volume for the combustion chamber, we can put energy input. This is coming out from the compressor. This we are representing in terms of fuel burning process, and we will be having the flue gas that will be coming out, and that will be with high temperature of T05 or enthalpy of H05. So, we can write down our energy balance. Based on this energy balance, we can calculate what will be our fuel air ratio. This fuel air ratio for turbofan engine, it is in correlation with m dot core, means what air, that is what is entering inside my core engine. Okay. So, from that we can calculate what will be our fuel air ratio, that is what is required in order to achieve that particular temperature. So, again be careful, maybe you will be given with the turbine entry temperature, or maybe you are given with the fuel air ratio. So, accordingly you need to select your formulation and you need to calculate either fuel air ratio, or maybe you need to calculate what will be my turbine entry temperature. Okay. Now, let us try to understand next terminology. So, here if you look at, it says the bleeding of air from the engine. So, if you look at carefully, at some location in HP compressor, we have taken the point tapping out, and that is what I have defined as say air bleed, and that is at the pressure of P03B and say temperature of T03B. Now, the question may arise, why do we think of air bleeding here? So, any idea? Do you have any understanding of this? So, most of the engines what we are using currently for our commercial aircraft, even for fighter aircrafts, this bleeding, that is what is very common. So, some amount of air, maybe say around say 2% to 20% air, that will be bleeded from the HP compressor. In some engines, air may be bleeded from LP compressor also. So, it depends on what is a kind of design that designer has done for this particular engine. So, let us see what is the purpose of that. What it says, the bleed air from the system, it is been used for internal cooling of the engine. So, here if you look at, many times we used to say we need to cool the turbine blade. When we say we want to cool the turbine blade, we need to have the cool air, because what gas is coming out, that will be at very high temperature and very high pressure. So, at same pressure I need to inject my air for the cooling purpose, otherwise you will be having the reversal of the flow. That is the reason why we are looking for high temperature and high pressure air to be injected here. So, that temperature, we can say the pressure we will be taking from the HP compressor is similar to say the exit pressure here for HP turbine. Temperature that need to be lower in order to cool down the blades. They are also being used for the cross starting of the engine. Suppose say we are fitted with say 2 engines or 4 engines, then maybe in order to start that engine we can use that. Same way we can use that for the engine or the end airframe anti-icing. So, when we are flying at particular altitude, there may be chances that icing will happen. So, in order to avoid that, for anti-icing we are using this compressed air. It is also been used for cabin pressurization. So, when we are flying at higher altitude, we may be feeling some kind of uneasiness, that is what is because of very low pressure. So, we will face the problem in terms of breathing. So, that is the reason why pressurization is required. Same way some pneumatic actuators, air driven motors, pressurizing the hydraulic reservoirs, waste and water storage tank. So, all this required additional amount of air, and that air is compressed air, and for all these purposes we need to take out the air from the engine, and that is what is called bleeding of air from the engine. Okay. So, let us see, this bleed air is compressed air taken out from the aircraft engine for cabin climate control. So, as we have discussed, at higher altitude we need to have auxiliary breathing air. If we will not be having that, then maybe we will be suffering from hypoxia or oxygen starvation. One more idea is bleed from the HPC, that will be increasing the surge margin by lowering the operating line, and this bleed is injected in the bypass stream, then we will be having lower losses, but it has sometimes reverse impact also, inverse impact also, that will be reducing the surge margin of the fan. Okay. Now, here if you look at this, is giving very good idea in terms of what all will be the use of what we say in terms of bleeding of the air. So, here at inlet there are chances for the icing, same way here we are having the chances for the icing on the leading edge of the wing, same way some pressurization for actuating mechanism, that is what is required. So, these all are the purposes for which we are taking the bleed air out from the engine. This bleed air is also used to heat the components such as rear frame. So, like we will be having differential pressure, differential temperature, that is what we say thermal gradient. So, in order to avoid that, we need to have the hot air to be used. Similarly, pressurized cavity upstream and downstream of the disc to offset the axial load generated by the blade as well as vent, and that is what will be supporting our axial thrust. So, in order to manage that, the pressurized air it is being used. Same way, pressurize certain cavities in seal and prevent the ingestion of hot gas to purge certain system or to remove the debris or the local cooling. In order to cool the say oil, sometimes it is also been used to maintain the tip clearance. So, all these are the purposes. So, there are many purposes for which we are bleeding the air from the engine, and we need to be very careful about doing the cycle analysis. So, let us see where exactly it will be reflecting in our cycle analysis. So, let us look at here. Say here we are having this as our combustion chamber process. Here in this case, if we look at, say this is our combustion chamber and certain amount of air it is being bleeded from this engine, and that is what we are writing as say m dot core minus B. So, this B is nothing but it is a ratio of mass of the air bleed through the compressor divided by core air flow. So, that is going inside. So, that is what will be reflecting here in terms of m dot core plus m dot F minus m dot B into H05. So, be careful when it is given that the air it is being bleeded from the HP compressor, then you need to modify your energy balance for the combustion chamber, because very first component after air bleeding will be your combustion chamber. Okay. So, if we are writing the energy balance, we will be having the formulation, that is what will be changed. It is in multiplication of 1 minus B. If you compare your previous equation where we are having H05 minus H04 divided by burner efficiency into calorific value minus H05, and here my fuel air ratio, that will be say in multiplication of 1 minus B. Okay. So, very important parameter here we are calculating is the fuel air ratio for that. Now, let us move towards the next component, that is our HP turbine. For this HP turbine, suppose if I consider there is no air bleed, I am specifically mentioning here without air bleed. So, what we know, this HP turbine that has been used for rotating the HP compressor. So, if I will be writing my work balance, this is given by m dot core into 1 plus F Cp T05 minus T06, that is what will be equal to m dot core Cp T04 minus T03. Now, based on this balance, we can calculate what will be the temperature at the exit of the HP turbine. Similarly, we want to calculate what will be the pressure at the exit of HP turbine. For that, we will use the efficiency formulation, and from this efficiency formulation, we will be calculating what will be our exit pressure from the turbine, HP turbine. Okay. Now, suppose if I consider I have my bleed air. So, I am giving you some time, let us see, like just try to write down the work balance. This work balance, it says like we have taken our air from the compressor at location 3B. Okay. So, can you please write down the formula for work balance between compressor and HP turbine? Okay. So, let me put this equation. What will be the change? Here in this case, my mass flow rate through my HP turbine, that will be 1 plus F minus B Cp delta T0. Same way, there is here in this formulation, I am writing this as say we have taken our air at some location T03B. So, that is the reason we are writing m dot core Cp T03B minus T03. After this stage, by mass flow rate that will be reduced, that is why we are writing m dot core Cp 1 minus B T04 minus T03B. Be careful in writing this equation. This is very important here. Okay. So, just understand, suppose say after third or fourth stage, suppose I am putting this location as say T03B and P03B, then my formulation will be m dot core Cp T03B minus T03, and for the remaining part it will be 1 minus B that will be added here. Okay. Now, this is what we say in terms of writing the equation for HP turbine, and from that we can calculate what will be the exit temperature from the HP turbine. Okay. Similarly, we can calculate the exit pressure based on our efficiency term. So, we will be calculating our exit pressure and exit temperature from the HP turbine for bleeding case. Same way, suppose if I consider say LP turbine, again I am writing here it is without air bleed. When I say without air bleed, this LP turbine, as per my configuration, what we know, this LP turbine, it is been used to rotate my LP compressor as well as fan. That is the reason my work balance will be W LP turbine, that is what is equal to W of fan plus W of say LP compressor. So, let us put the equation. This is given by m dot core 1 plus F Cp T06 minus T07. Similarly, for the fan, be careful, this is what is given by beta m dot core, it is m dot F basically into T10 minus T02, and here this is what is for our compressor. So, here in this case, let me write down this equation, this as say T03 minus T02. I am writing down this equation in terms of say adding and subtracting T010. I am doing this purposefully. When we are doing this, the formulation that will be changing here. So, be careful about this formula change. Okay. So, here if we are writing this equation, based on that we can calculate what will be our exit temperature from the LP turbine. Now, we have formula for our efficiency. Based on that efficiency, we can calculate what will be the exit pressure from the LP turbine. Now, let us put the equation for say bleed case. Here in this case, bleeding, that is what has been done at station 3B. Similarly, I will be writing the equation for work developed by LP turbine, that will be work consumed by fan plus say LP compressor. Now, here in this case when we are having bleeding, we need to be very careful the amount of mass flow rate or mass flow rate passing through my LP turbine, this will be changing here. So, I have removed this m dot core part on in terms of balancing on both the side. So, do not get confused by this equation. Okay. And here this is representing by beta Cp T010 minus T02, and this is representing my LP compressor work. And if I will be writing this in terms of simplification by adding and subtracting T10, this will be my overall formulation. And based on that, we can calculate what will be our exit temperature from the LP turbine and what will be our exit pressure from the LP turbine. Okay. So, we need to be very careful here in terms of doing all the calculation when we are having bleeding case. We will solve the numerical also, that is what will be giving you confidence in terms of consideration of the air bleed. Here you may be having question, say sir, suppose say 2 to 5% of air we are taking from say HP compressor, and that is what is being used for the cooling of HP turbine. So, be careful under that configuration, this mass balance will be again it will be retaining. So, whatever that is what has been lost from the HP compressor, that is what will be gaining here, and for LP turbine it will be similar. But the chances for using of this bleed will be 2 to 5% only. Majorly this bleeding of the air, that is more than maybe 10% or maybe it is around in the range of 20%. Okay. Now, what we have is our tailpipe, and for this tailpipe we know we will be having drop of pressure, and that is what will be giving you the outlet pressure as P08. Similarly, the process we are considering as a adiabatic process. So, my temperature will be T08 equal to T07. Now, in terms of nozzle, we have two nozzles here, that is what has been represented by process 8 to 9, and second that is what is from 10 to 11. And here in this case we can say we will be checking very first whether our nozzle is choked or unchoked. That will be done based on say critical pressure calculation and ambient pressure. So, let us calculate what will be the critical pressure ratio for our turbine nozzle. It is P08 by Pc. Since our nozzle efficiency for the turbine nozzle is known to us, based on that we will be deciding whether our nozzle is choked or unchoked. We know now when we are having our critical pressure lower than the atmospheric pressure, then we are considering the exit pressure as atmospheric pressure, and we will be calculating our temperature ratio. Based on that temperature ratio, we can calculate what will be our exit velocity. Similarly, suppose if I consider say nozzle is choked nozzle, where my critical pressure is more than the atmospheric pressure, under that configuration our exit pressure will be equal to critical pressure. Similarly, we can calculate our temperature ratio and we can calculate what will be our exit velocity. In line to that, we can do our calculation for the fan nozzle. Here in this case, the critical pressure ratio will be P010 divided by Pc. For that also nozzle efficiency, suppose it is known to us. From that we will be deciding whether critical pressure is higher or lower than the atmospheric pressure, and we will define this nozzle as choked or unchoked nozzle. Based on that, we will be calculating exit static temperature and we will be calculating what will be our exhaust velocity from the fan nozzle. So, this all are called our cycle parameters. Now, we are more interested in terms of calculating the performance parameters, and this performance parameter very first is our thrust, and here for the turbofan engine we are writing that as a cold thrust plus hot thrust. What we mean by cold, we know now it is in terms of what air that will be coming out from the fan. So, it is m dot fan into V10 minus V infinity. Similarly, this is representing my pressure thrust. In line to that, suppose if I consider for the hot thrust, say that is given by m dot core into bracket 1 plus F V9 minus V infinity, and this is representing my pressure thrust from the say turbine nozzle. Now, formula we need to be very careful here. Suppose if you are considering the case with the bleeding, you should not commit the mistake. We are having the formula, that is what will be changing here, and that is what is 1 plus F minus B. Okay. So, be careful, and B, as we have discussed, it is nothing but the bleed air divided by my core air. Okay. Same way here in this case, we can calculate our thrust specific fuel consumption. This thrust specific fuel consumption, it is given by F into m dot core divided by thrust. Propulsive efficiency in the configuration with say bleeding, we can write down the formula here. Similarly, we can calculate what will be our thermal efficiency, and once we have our propulsive and thermal efficiency, we can calculate our thermopropulsive efficiency or overall efficiency. So, you must realize what all we are discussing here, in which my compressor and fan, they both are on the same shaft. So, we will be having change in our formulation for the work balance. We are having say bleeding, under that configuration we will be having change in our energy balance as well as work balance, and performance parameters also will be different compared to non-bleeding kind of configuration. Okay. Now, let us look at, this is a kind of engine, say it is called short takeoff and landing for the fighter aircrafts. So, mainly for marine application, this kind of engine configuration have been selected. So, here if we look at, we are having say variable pitch fan, that will be followed by LP compressor. Here we are having HP compressor, HP turbine and LP turbine. The difference here in terms of what all we have discussed earlier is the air, it is been bleeded from, it is been bypassed from this LP compressor, and that air it is been supplied to the say our wing. In this wing we are having say augmentation of the flap system. So, basically this compressed air, it is been used to enhance the lift capacity of this particular aircraft. So, this also is possible. So, as I discussed, based on our understanding, based on our requirement, we can configure our engine. So, this is of a special kind of engine or special class of engine, where rather using say HP compressor air, LP compressor air, it is being used. Okay. So, here we are stopping with this particular lecture, and I am sure now you have understood what we mean by the types of turbofan engine. Specifically, we have started discussing the two spool configuration, that is unmixed two spool configuration, in which my fan and compressor, they are been on same shaft, and that is been rotated by LP turbine, and HP compressor and HP turbine, they are on other shaft. So, in next lecture we will try to solve numerical, and then we will start discussing the next configuration of the engine. Thank you very much.